All right, in this video, I'm going to go over grain counting that will be part of Lab 1 annealing of cartridge brass. So I have open our Lab 1 handout, which you can find on our Canvas page. And there's a lot of obviously useful information here, but I want to skip down to the last section, which talks about grain size determination. This is from ASTM E112-10, and it walks you through the procedures in that ASTM, hopefully a little bit more simplistically and a little bit more step by step than it would in that thing. So I just want to walk through and give you an intro, and then we'll go through an example of how to determine grain size. So obviously, grain size is one thing that we want to get about our micrographs for this lab annealing cartridge brass. We want to see how big those grains are and compare them to other conditions. So we're obviously going to need to have photomicrographs for each of our specimens that we're interested in looking at, and we can print a copy. This semester that's a little harder, but that will be possible if people want to do that. But I'm going to show you a way to do this on the computer. So things that we'll get is we will be able to get a grain size number, which correlates to the grain size of the sample. So it'll allow us to compare that. And another useful feature that we're going to look at that's particularly useful for our set of samples is this anisotropy index. So this allows us to compare the intercepts in the parallel and perpendicular directions to the rolling direction so that we can see or measure the effects of rolling, right? So this is particularly useful in this lab. Oftentimes, the grain size is harder to calculate because of the heterogeneous nature of our materials, but definitely you want to get this anisotropy index. So this video will show you how to go through and perform these tasks using ImageJ. So as a refresher, ImageJ is a free software. I have it open on my computer right now. You can get it online, and I made a video for MSE407 last semester that details how to use it for basic operations. So if you are unfamiliar with ImageJ, if you weren't in MSE407, go back to my YouTube page and find the video that is for ImageJ tutorial. I've also added it to the 408 playlist in YouTube, so you can find it there if you're struggling to find it. So we'll then now walk through a demo of how to get these quantities during grain counting for this first lab. Let's look at the first part of this. So we're going to assume that we already have the photomicrograph ready to go. We have a picture of it. We've loaded it into ImageJ, but I want us to come back to this equation. This first equation is for the mean linear intercepts. So if we're drawing a line or a circle, there's going to be intercepts of that line with the grain boundary. And so the mean linear intercept is basically an average of that, which we can relate to the grain size. So to know this equation tells us we need to know capital L, which is the length of our line or the perimeter of our circle. We need to know the number of these grain boundary intercepts by counting them, and we need to know the magnification of the images. So this is if we're doing this on a piece of paper, but we're going to be using ImageJ, and so this becomes even more simple. And so we're going to go through how we do that. So effectively, our magnification will be calculated by ImageJ, and all we have to do is measure the length of a line using the built-in function and then count up the number of intercepts. And so that's what we're going to do next. All right, before we get into ImageJ, I just want to refresh and show you the equation that we just talked about for mean linear intercept. That's what you saw in the handout. And then and this is the micrograph, just a simplistic micrograph. So our intercepts are the boundaries. So this is just a simple line of length L, and then our intercepts are here and here with a line drawn, right? So we need to know magnification, number of intercepts, which is in this case 2, and then we need to know the length of the line L. So that's the traditional way. But in image J, we can simplify that to just the length over the intercept number if L is set to microns and the scale of the image is set using the scale bar inside image J. And so that's the part I'm going to show you. But this basically this equation kind of becomes simpler, and I'll show you the procedure in image J next. Now let's go and use image J to do this calculation of mean linear intercept. So I'm starting from my home screen. This is on a Mac, so there's probably going to be a few minor differences if you're using this on a PC. But I already have image J open up here, just a very simple toolbar right now. You can go to File, Open, or if you have the image, which I'm going to use this one, you can sometimes drag it directly in. So now it is open within image J. This is the picture that I'm going to be dealing with. So this is what we're going to look at. All right. So the first part I want to look at is the part that simplifies that equation for us. So we want to set the scale of the image. So you'll notice that all of your images should have a scale bar. If it doesn't, that's obviously an error, and please let us know. But this is a scale bar. So this is telling us that this distance on the image equals 50 microns or micrometers, right? So we want to apply that, and that tells us what the magnification is, right? So that's basically the M part of this equation. So we can use image J to make our lives a lot easier. So I'm going to use the zoom tool, and I'm just going to make this pretty big so I can really see it down here, right? You can even see the pixels at this point. All right, and I'm just going to make this window a little bit bigger and maybe zoom it in one more time. There we go. Super big. So this way, the more zoomed in you are, the better you're going to be able to tell where the line ends. And this will hopefully help with any sort of error associated with drawing lines. So next thing I'm going to do is I'm going to select the line tool, which is up here. So that's selected. And I'm going to make a line that is the length of our scale bar. And again, get as close as you can to this. Try to get it as straight as possible. All right, so to spend a little time, make sure you have that representing the length of the scale bar, right? So my line matches that black line, which tells me that it's 50 microns. So leave that for now, and you're gonna come up to Analyze, and you're gonna see a set scale. So click the set scale, and in here, this is where it basically sets the scale of the image and allows us to, in essence, it tells us the magnification, but it converts, what 1 pixel equals in this scale of the image, right? So it's telling me what that pixel is worth. And so the line I drew, it's going to come up and automatically fill this. So the line I drew is this number of pixels. So basically 79 pixels. Right now it says 0 distance, but we know the distance. That's the scale bar. So we're going to put in 50. You can put in 50.0 if you want, but it's 50. So 50 microns equals that many pixels. And then down here, it says unit of length. We know this to be microns. Obviously, you can't put Greek letters in here, so usually just use UM for micron or the symbol there. So now down here it says that basically 1.6 pixels is the same as a micron, right? So now if we draw lines on this image, we will be able to know the distance because we have set the scale. And that's why we can eliminate the need for the magnification in our equation. And if we use the tool in image J to calculate length, then that will give us capital L in microns, and this will be allow us to calculate the mean linear intercept without the additional need for the other steps. So now I'm going to zoom back out. Again, you can use the magnification image here. You can also use the control or command keys. And I'm going to come back out. And this is my full image. All right, so now we want to start the analysis and start the calculations. So again, the two things I need to know are how many intercepts I have over a given length. So that's what we're going to do. But I also want us to think ahead, because we're going to look at this anisotropy index, which they say as AI. And this allows us to quantify the level of rolling, right? Because the more elongated we can see with the anisotropy index. So what that means is we need to identify the rolling direction. So if you're the one taking the image, you should always note how you're loading the sample so that you know the rolling direction. In some cases, it's going to be obvious. So in this image, you can see that the grains are flattened in this kind of general direction. They're slightly longer. And so that's my rolling direction across the horizontal of this screen, right? So in the lab, we are going to come up with a system, and all of our images will be oriented the same way so that you don't have an issue with the direction there. But in this case, we can kind of see that from the image itself, that it's generally rolled along this direction. So for the anisotropy index, I'm going to want to draw lines parallel to that direction and then also perpendicular to that, because that will give us a measure of how flat and how elongated they are. So that I just wanted to give a heads up, because that will sort of dictate what types of lines we draw. So we can draw a line, right? So I can just go back. I'm in the same tool up here for lines, and I can just draw a line of, random length along that direction, right? So that's my line. Or I can draw one perpendicular like this, and that would be my line. So that's what we're going to do. So the first step, if you're given, if you have a given line, the first thing I would do is calculate the length of that line. And that is something that the computer is going to do for you. So again, go back up to analysis and hit, this time, measure. You'll also see the shortcut for it too if you want to do it that way. Now you've got the results box here. It's going to give you, it's going to collect all the measurements that you do. And it's going to tell you a lot of different information. A lot of it doesn't matter. So we're doing a line, so area doesn't matter. Don't worry about the mean, min, max, any of that. Angle can be useful. The angle is basically the orientation in the image, so that can help you identify whether it's perpendicular or parallel. And then the length. This is going to be the important part, right? So right now, the way I've drawn the line, it is 372.571 microns long, right? That's why we don't need to do the additional magnification, right? So that's my length right off the bat. All right, so that's what you're going to do for every line that you draw in image J. All right, the next step would be then to measure the length. And I just erased my line, so I'm going to start over again. Let's do this. All right, again, you can see in the background there, it's slightly longer than the last one, but roughly the same orientation, right? So now you've got the length. You can write that down for your calculations. And now you're going to want to count the number of intercepts. So this is the part, where you're going to manually go through and count these lines. I welcomed, I know there's some sophisticated programs out there that will do this for you. I want to sort of show you the manual route, but keep in mind that there typically are ways of doing this portion for you. So let me zoom in a little bit, and we'll kind of scroll through, right? So basically, when you see a boundary, you're going to count it, right? And this is where it can get tricky. You know, there's going if two people count the same thing, they might get slightly different results. And so let's just sort of go through and see what we see. Um, so this one right here, this looks like a boundary between this grain and this grain. So I'm going to count it. One, and we got another one here. This line right here, to me, looks like it's within a grain. The contrast between these two sides is the same. This thing kind of terminates within. So it's either a scratch. I don't think it's a scratch, but it looks more like this, right? All this stuff's within a grain. So I'm not going to count all these little marks as a grain. So we've got this one, not this one, this one, this one, this one, this one, right? And you'd want to keep track of these as well. And you keep going. And again, try to differentiate these different features from one another. I will say it's pretty hard. I took a real image that we had from last year. And so you can see that there's already, this area is a little fuzzy. How do we count that? To me, it looks like we have one here, another one here. I would probably count this. It looks like this is a boundary too. Here, 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 and I think potentially here and here, here. So as you can see, you keep going and you'll get all of these. So again, there's going to be issues depending on how good the images are and what features you can differentiate, right? These lines in here are not grain boundaries. If you see what we call twins in some images, those are not. If you see a scratch, obviously don't count that. And so it can get a little fuzzy. So I recommend that multiple group members try to attack the same problem and see what you get, right? And that kind of goes into the error of this method. And so there will be error bars, and use your multiple counts for the same line as a way of looking at that. All right, so you'll want to collect all of those points that you marked. And that will be your term N sub L, which gives you your number of grain boundary intercepts. So knowing those two things, you can calculate the mean linear intercept length for a given line. And you can also collect them all for a given image. So if we do multiple lines, chances are we'll need multiple lines. So we can do multiple lines in this direction and multiple lines in the parallel direction, and we'll have information for those later calculations. All right. I want to show you a couple of tips and tricks that might help you with this counting procedure that you're going to be involved in, because I showed you one, but as you can imagine, you and your group are going to be doing a lot of these. So consider these couple of tips. Maybe they help things out. So I'm going to show you a couple different things. So I can draw a line as I showed you, but if I try to do anything else, right, it's going to erase that line. So you have to be careful not to click anything, right? So that can be an issue. So let's say I have a line and I want it to be more permanent, right? So I made that line just like I have before. I'm in this tool up here and I draw that line. So if I go to edit and I hit draw, or again, use the shortcut, that's going to put it on more permanently. So now you'll notice if I click away from it, it's still there. So you can always do something like undo if you want to get rid of it. So there are ways you can get rid of it. So it's not there forever, but it is more permanent. And so the reason I mentioned that is, let's say you already drew the line, you already calculated the length like we did before, but you're getting to the counting of the intercepts and you can't keep track of them, right? So I do this feature, the edit draw, it's permanently there now. And let's now shift to this other icon that says multi-point, and you can see that there's like 5 points on it, right? So let's click that. And again, I'll zoom in so I can start, right? And here I can click a point where my first line is. This is where my second, third, and I keep clicking the multi-point feature everywhere that I see an intercept, right? So now it's counting it for me. So that would be one way I could keep track of those intercepts if it's hard to do manually. So in this case, excuse me, we have lots of points, and so you may lose track eventually. So this is one way to replicate what you might do on a piece of paper by making a dot, right? So you could use this multi-point feature. So that's one tip you could potentially do for making this go easier. Through the ImageJ sort of demo of how we can calculate the number of grain boundary intercepts and calculate the length of line. And this would allow us to, again, solve for this equation very directly. Again, keep in mind our modification we had with M. And then very easily we can get the area from this equation. So just basically inputting the mean linear intercept, we can get the average planar area. So this is something that potentially you'd want to look at. So this tells us roughly what the area of a grain would be. And then based on another equation, we can calculate the grain size. So this is diameter D from that term, the mean intercept length. So we can calculate that as well. But often what we really look for is this ASTM grain number, G. And again, it's just a simple equation related to the mean linear intercept. So when we calculate that for a sample, then we can calculate the grain number, which is something we can compare sample to sample. So that's one thing we can get. The last thing I mentioned, right? So this is where, if you're doing, if you're trying to get how anisotropic the sample is, how rolled it is, in another word, this is what we're going to use, right? So this is where we want to keep track of those mean linear intercepts that we do parallel and perpendicular to the rolling direction. And so we keep track of those, and then we're able to calculate this index that we have here, and this will tell us whether we have and more rolled, less rolled, or more isotropic. So there's really no sign of anisotropy, right? So these are all things that we can calculate just from these mean intercept links that we just got. So keep track of those values as you're going along. And then also, again, I put a very basic structure of how to solve or how to go through and solve for this. But keep in mind, you can always go back to this ASTM. I put this in our folder, and you can find it, and it'll give you more detail if you're wondering some more specifications for this, because I haven't sort of given you everything, all the little tidbits and stuff. So definitely go to the ASTM to check that out a little bit more. And it also gives you some more information for how to find statistically significant results. You're going to want to get a lot of intercepts per length. So don't use, you don't typically want to use super high resolution unless your grains are very small. And so I put the statistical error equation here for you as well. So yeah, so these are some of the things that you're going to want to do, and this is just a quick demo tutorial for grain counting. And the new kind of revelation from what you've done in other courses is going to be this anisotropy index, which allows us to look at that rolling and characterize it. So if you're looking at 0% all the way up to 60% cold work or rolling reduction in thickness, then we can see if that how that translates on the micro level with this anisotropy index.